This is week 5, data compression. Lecture notes in information theory. I'm Hikmet Kamberay, professor at the Faculty of Engineering, International Balkan University. An outline of the lecture for today includes data compression, Kraft's inequality, optimal codes, where I'm going to talk about the Hoffman codes and Shannon Fano-Elias coding. By definition, a source code C of the random variable x is a transformation from the set chi, a range of x, to the set D star, the set of finite length strings of symbols from D array alphabet, where D it is equal to set 0, 1, 2 up to D minus 1. C it is this function from chi to D star, and it is such that C, little c, it is equal to the big C of x, where x is a realization of the random variable x, and little c denotes the code word corresponding to a random variable x with length L of x of the code C of x. If you want to represent it graphically, this will be a transformation from the set chi to the set D star, such that to each element x from chi, it associates another element, an image, C, which is equal to big C of x in the D star. And the big C represent a function from chi to D star. As an example, consider a random variable x drawn from the set chi, which is the set of elements red and blue, with alphabet D, which is the set of 0 and 1, such that C of red, it is equal to 0, 0, C of blue, it is 1, 1. Then we can see from this one that the length of the red and length of the blue are both equal to 2, and it includes number of zeros or 1 on each code word. The expected length, by definition, expected length L of C of a source code C of x from a random variable for a random variable x with property mass function P of x is given as sum of all x's from chi P of x times L of x, where L of x is the length of the code word C of x associated with x. As an example, let's calculate the entropy of a random variable x and the length of the code word of the random variable x with the following distribution and code word assignment. Probability that x it is equal to 1, it is 1 over 2, and the code word of x being equal to 1, it is 0. Probability of x being equal to 2, it is equal to 1 over 4, and the code word of C of 2, it is 1 and 0. Probability of x being equal to 3, it is equal to 1 over 8, and the code word C of 3, it is equal to 1, 1, 0. Probability of x equal to 4, it is 1 over 8, and the code word C of 4, it is 1, 1, 1. Now, if we calculate the Shannon entropy, h of x, we use the formula minus sum of all x's from chi, P of x, log with base 2 of P of x. This is equal to minus 1 over 2 log with base 2 of 1 over 2, plus 1 over 4 log with base 2 of 1 over 4, plus 1 over 8 log with base 2 of 1 over 8, plus the same 1 over 8 log with base 2 of 1 over 8. Then these converse equal to minus 1 over 2, minus 1 over 4 times 2, minus 1 over 8 times 3, minus 1 over 8 times 3. And this becomes 4 plus 4 plus 3 plus 3 over 8, 7 over 4, and it is equal to 1.75 bits. Now, if we calculate the expected length of the code word C, then we use the formula sum of all x's from chi, P of x, L of x, and this is equal to 1 over 2 times 1, plus 1 over 4 times 2, plus 1 over 8 times 3, plus 1 over 8 times 3, and this becomes 4 plus 4 plus 3 plus 3 over 8, 7 over 4, equal to 1 over 1.75 bits. We can notice that L of C it is equal to the Shannon entropy H of X. Now let's take another example. We calculate the same Shannon entropy and the expected length of the code word C of the random variable X with the following distribution and code word assignments. Property of X being equal to 1, it is 1/3, and the code word C of 1, it is simply 0. Property of X being equal to 2, it is 1/3, and the code word C of 2, it is 1 and 0. Property of X being equal to 3, it is 1/3, and the code word C of 3, it is equal to 1, 1. For the Shannon entropy, we use the formula minus sum of all x's from chi, p of x, log with base 2 of p of x, which is equal to minus 1/3 log with base 2 of 1/3 plus 1/3 log with base 2 of 1/3 plus 1/3 log with base 2 of 1/3, and you get minus 3 times 1/3 log with base 2 of 3, which is approximately equal to 1.58 bits. Now the expected length of the code word, it is equal to the sum of all x's from chi, p of x, L of x, which is equal to 1/3 times 1 plus 1/3 times 2 plus 1/3 times 2, which is equal to 1.66 bits. And you could notice that L of C, it is slightly greater than H of X. How much is the upper limit? We'll discuss this one. There is an exact upper limit on this. We can give now the definition of the so-called non-singular code. A code is called non-singular code if every element in the range chi maps into a different strings in D star. This would mathematically be written as for every x from chi, for every x prime from chi, whenever x is different from x prime, then C of x, it is different from C of x prime. Now, since the transformation C from chi to D star is a function, then a non-singular code represents a one-to-one or injective function based on what you might have learned on mathematics. This would mean that if I pick up two x and x prime, a pair x and x prime from chi, such that x it is different from x prime, each of these, it is mapped according to the function C into one in C, little c equal to C of x, and the other C prime equal to C of x prime. Then since x it is different from x prime, also this implies that C it is different from C prime. This would mean non-singular code. Now let's illustrate this with an example. Consider x to be a random variable with the following distribution and code word assignment. X equal to 1 as a code word C of 1 equal to 0. X equal to 2 as a code word C of 2 equal to 0, 1, 0. And x equal to 3 as a code word C of 3, 0, and 1. And x equal to 4 as a code word C of 4, 1, and 0. Suppose that I have this sequence of bits 0, 0, 1, 0, 1, 0. I want to decode this one into a sequence of symbols of x. Now you could notice that there is not a unique decoding of this. So the string can be ambiguously decoded into the following symbols of x. Initially, we can take 0 in red and decode it into the symbol 1. Then we can take the 0, 1, and 0 in blue and decode it as 2. Then 1 and 0 left, we decode it as 4. So this would be the sequence of symbols 1, 2, and 4. However, equally, probably could also be the following sequence of symbols. Again, we decode 0 as 1, as shown in red. However, we decode 0 and 1 now, shown in blue, as 3. Then again in green, 0, we decode it as 1. Then the last 1 and 0, we decode it as 4. And we get the sequence of symbols 1, 3, 1, 4. We can go probably also in this way. On the third row, we decode again 0 as 1. Then we decode 0, 1 as 3, as shown in blue. Then 0, 1, 0 as 2. And we get 1, 3, and 2 as a sequence of symbols of X. Or we could have gone in this way. Again, 0, first 0 decoded as 1, shown in red. 0 and 1 in blue decoded as 3. And then 0, 1 we have decoded again as 3, shown in green. Then the last 0 as 1. And we get the sequence of symbols of X, 1, 3, 3, 1. So we can notice that there is an ambiguity on decoding the string of the bits given above. All right, would have been any of these. Now, in practice, to avoid this one, if one uses the non-singular coding, it is to add an extra character, for example, a comma, and this may remove the ambiguity. However, this could be a problem because you are sparing an extra character. So practically it's not useful, right? It's not something. However, can be done. For example, if I write it, this sequence of bits in the following 0, 0, 1, 0, 1, 0, then this would have been uniquely decoded into the sequence of symbols 1, 2, and 4, and there is no ambiguity on this. Another definition, it is extension code. Extension code C star of a code C is the mapping from finite length strings of chi to finite length strings of D, defined in the following. C of x1, x2, and so on xn. It is C of x1, C of x2, and so on C of xn. Here, C of x1, C of x2, C of xn represent the concatenation of the corresponding code words. For example, let C of x1 be 0, 0, C of x2 be 1, 1. I want to determine C of x1, x2. By definition, C of x1, x2, it is concatenation of string C of x1 with a string C of x2. And this would mean then C of x1, x2, it is the sequence of bits or the string 0, 0, 1, 1. Another definition is uniquely decodable codes. A code is called uniquely decodable if its extension is non-singular. In other words, an encoded string in a uniquely decodable code has only one possible source string producing it. All right, and this avoids ambiguity. However, there is a problem on this that I'm going to describe in the following. Consider X to be a random variable with the following distribution and code word assignment. X equal to 1, it is as a code word of C of 1 equal to 1, 0. X equal to 2 as a code word C of 2 equal to 0, 0. X equal to 3 as a code word C of 3, 1, 1. And X equal to 4 as a code word C of 4 equal to 1, 1, 0. Now, if the string on here starts with either 1, 0 or 0, 0, then these 2 bits are decoded immediately. For example, 1, 0, it is decoded as 1, and 0, 0 as 2. However, if the first 2 bits are 1, 1, then there is a problem, because 1, 1 could be 3. However, depends on the next bit. If the next bit would have been 0, then this could have been equally probable to be also 4. All right. Now, if the following bit, in that case, if the following bit it is 1, then the first 2 symbols can be decoded as 3. If the next bit it is 0, then we have to check the length of the string immediately following 1, 1. If it is odd, then the code it is 1, 1, 0 and corresponds to 4. If the length of the string immediately following 1, 1 it is even, then the code word it is 1, 1, which can be decoded as 3, and so on. So the drawback of the uniquely decodable codes, it is the last case, because we have to calculate or to count the length of the string immediately following 1, 1. And this could be some time overhead. All right, so it is mostly on the computation time. For example, suppose that I have the string of bits 1, 1, 0, 0, 1, 0, 1, 0. Now, these can be uniquely decoded into the following. 1, 1, using the code before, it is 1, 1. Now, you could see the next following, it is 0. However, the code number of that is following, it is 3, 6. So it is an even number. Then this, it is decoded into 3. And what is left, it is 0, 0, 1, 0, 1, 0. Then next one, it is 0, 0, which is decoded as 2. Then a remaining one, it is 1, 0, 1, 0. Then you could check that 1, 0, it is decoded as 1. Then I obtain the sequence 3, 2, 1, and the last bits are 1 and 0, which are again 1. Then I get the final 3, 2, 1, 1 uniquely. Another type of code, it is the so-called prefix code. A code is said to be a prefix code or instantaneous code if no code word is a prefix of any other code word. Consider X to be a random variable with the following distribution and code word assignment. X equal to 1 and the code word C of 1 it is equal to 0. X equal to 2 and the code word C of 2 it is 1, 0. X equal to 3 and the code word C of 3 it is 1, 1, 0. X equal to 4 and the code word it is C of 4, 1, 1, 1. Now this encoding is a prefix code, and you could notice that there is no code that is prefix of any other code words. So none of these, so the first is 0, but none of the others start with 0. The next one, it is 1, 0, but none of the following start with 1, 0. Next one, it is 1, 1, 0, and none starts with 1, 1, 0. Let's consider this string of bits 0, 1, 0, 1, 1, 0, 1, 0. Then this can be instantaneously decoded in 2. You could notice the first 0 can be decoded as 1. Then the next one, it is 1, 0, can be decoded as 2. Then the next one, it is 1, 1, 0, which can be decoded as 3. Then what is left, it is 1, 0, which can be decoded as 2. Next, I'm going to talk about the so-called Kraft's inequality. For any instantaneous code or prefix code over an alphabet of size D, that is, the D, it is the set of bits 0, 1, 2, and so on up to D minus 1. The code word lengths L1, L2, and LM must satisfy the inequality. Sum of I, D to the power minus Li, it is less equal to 1. Vice versa, for a given set of code words with lengths that satisfy equation 5, there exists an instantaneous code with these word lengths. First, we can start building up the so-called code tree for the Kraft's inequality. Always you start with some root. Then the following nodes from the right to the left include the bit 0, 1, and so on up to d minus 1. Then the next branch again adds to the first bits 0 to the left, to the right, 1 to the right, and so on. So this means that if I go from the right 0, it extends to 0, 0 on the right and 0, 1 on the left. Then I can follow the next one. It is 1. 1 adds a 0 if I go to the right branch, and the 1 to the left branch, and becomes 1, 1 to the left, 1, 0 to the right. And so on, I can continue. Then on the next level, then suppose that I pick up 1, 1 and 1, 0. Now for 1, 0, then I'll have on the left, I'll have 1, 0, then I'll have edit here 1, then I'll have 1, 0, 1, but I have not written. I have written only the branches that follow 1, 1. 1, 1 on the right, I'll have 1, 1, 0. Then on the left, I'll have 1, 1, 1. So this will be the code 3 for the Kraft inequality that I'm going to use. First, we constructed DRE3, as we showed on the previous slide, where each node has D children. Branches represent the symbols of the code word, such that the first branches following the root are the symbols 0, 1, 2, up to D minus 1. Each branch ends with a leaf, and the path from the root to the leaf traces out the symbol of a code word. Prefix condition implies that no code word is ancestor of any other code word on the tree. We denote by Lmax the length of the longest code word. A code word at level Li is D to the power Lmax minus Li descendants at the level of Lmax, which are disjoint. The total number of nodes in this set satisfies this one condition. Sum of i's d to the power Lmax minus Li must be less equal to the d to the power Lmax. Now we can see that d Lmax on both sides do not depend on I on the left-hand side, and can cancel out with d to the power Lmax on the right-hand side. So on the right-hand side, I'm left just with 1, and on the left-hand side, sum of i's d to the power minus Li, which is a proof of the first part of the theorem. For the second part of the theorem, so this means the vice versa. Conversely, for any given set of code word lengths, let's say L1, L2, Lm, that satisfy equation 5, we can construct a tree code for that in the following way. We label node 1 of length L1 as the code word 1, right, which is the code symbol 0, and remove all the descendants from the tree. So this means that all the descendants of 0, which are shown here with dashed line, are removed. So all these are removed. Then next, we label node 1 of length L2 as code 2, which is the code symbol 1, 0, which is this one, right? And remove its descendants from the tree. So this means that we remove all these parts. All right. Then the next, we label node 1 of length L3 as the code 3, which is the code symbol 1, 1, 0, which is this one. And we remove all the descendants. All right. This means we remove all this one. All right. Then we can continue in this way. A prefix code is constructed in this way with lengths L1, L2, and so on. All these are denoted in red on the code 3 shown on the following, right? And this is what we wanted to show. Now consider x to be a random variable with the following distribution and code word assignments. X equal to 1, code word C of 1, it is 0. X equal to 2, code word C of 2, it is 1, 0. X equal to 3, the code word C of 3, it is 1, 1, 0. X equal to 4, the code word C of 4, it is 1, 1, 1. Construct the tree code for this one. Now you could notice that D it is equal to 2 on this case. So this means that the set D, it is 0 and 1. So this means that if I start with the root, then the next nodes, children of this one, will be 0 and 1. Then I have C of 1 code 0, then I pick up 0 and remove all the descendants on here of 0. The next one, it is 1 here. Then the children of 1 will be on the right will be 1, 0, and on the left 1, 1. C of 2, it is 1, 0. Then I keep 1, 0 and remove all the descendants of this branch. Then on 1, 1, I continue with 2 children. 1, 1, 0 on the right, 1, 1, 1 on the left. Now 1, 1, 0 and 1, 1, 1 are both code words. Then I keep both this one and remove all the descendants of the 1, 1, 0 and the code 1, 1, 1. Then what is left? It is the code tree for this code word assignment. Now let's show that it satisfies the Kraft's inequality. Now you could notice that L1 it is equal to 1, L2 equals to 2, and L3 and L4 are both equal to 3. Therefore, we can calculate d to the power minus Li for I from 1 to 4. Then this is equal to, since d it is equal to 2, I put a 2 here. Then L1 it is 1, then I have 2 to the power minus 1, plus d to the power minus 2, plus 2 to the power minus 3, plus 2 to the power minus 3. Then this becomes 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 8. Or it is 4 plus 2 plus 1 plus 1 over 8, 8 over 8, which is less equal to 1. So the Kraft's inequality is satisfied. Now let's define the so-called extended Kraft's inequality. So this would mean for a infinite set of code words. So for any countable infinite set of code words that form a prefix code, the code word lengths satisfy the extended Kraft inequality. Sum of I from 1 to infinite now, d to the power minus Li, it is less equal to 1. And vice versa. For a given set of code word lengths L1, L2, and so on, that satisfy equation 6, there exists an instantaneous code with these word lengths. Now, consider a D-array alphabet, D, which is the set 0, 1, 2, up to D minus 1. And the ith code word, let's say it is Y1, Y2, YLI. Now, this would mean that 0 point Y1, Y2, YLI is a real number. It's a decimal number, which can be expressed, this you might know from other courses, as the following. 0 point Y1, Y2, and so on, YLI, it is equal to the sum of J from 1 to Li, Yi times D to the power minus J. This formula you might have learned if you express a decimal number or integer number into the binary number, all right, and vice versa. All right, so this is something that you might have learned also before. Now we consider this kind of intervals now. Interval 0 point Y1, Y2 up to YLI, and 0 Y1, Y2, YLI plus 1 over D to the power Li for every I, 1, 2, 3, and so on. Now, these intervals are disjoint and are satisfy the prefix condition, which means that they do not overlap. All right, this is what it means, disjoint in this case. And they are, moreover, subsets of this big interval, 0, 1, because they never exceed 1. Assuming the lengths, we get the following. Sum of I from 1 to infinity, d to the power minus li, it is less equal to 1. Where comes this from? First of all, the length of each of these intervals that you see here, take this, the upper limit, and subtract the lower limit. Then what you are left, it is 1 over d to the power li. If you sum up all these infinite intervals, 1 over d to the power li, it's written as d to the power minus li. Then you get the left-hand side, I from 1 to infinity, d to the power minus li, less equal to. Now, the sum of all these infinite intervals in the largest interval that will give is the interval from 0 to 1. But what is the length of the interval from 0 to 1? It is 1 minus 0, which gives you 1. And you get the right-hand side of this inequality, which is a proof of what I wanted. Now let's prove the second part of the theorem. The vice versa, we reverse the proof. So we assume that exists L1, L2, and so on, that satisfies the Kraft inequality, which is this equation on here. Now we order L1, L2, and so on in such a way that L1 it is less equal to L2, L2 it is less equal to L3, and so on. For example, 1 less equal to 2, less equal to 3, and so on. We assign then the intervals to each of these, 0 to 1 over 2, excluding 1 over 2, 1 over 2 to 1 over 4, excluding 1 over 4, and so on. Now, if you check all this one, interval 0 to 1 over 2, this corresponds to the symbol 0. 1 over 2 to 1 over 4 corresponds to the symbol 1, 0, and so on. Now, all this one satisfy the prefix condition. All right? Prefix condition that we just said it before. So this is the proof of the second part of the theorem. Now, let's give the optimal codes. The problem is the following. I want to find the lengths L1 star, L2 star, and so on, Lm star, satisfying the Kraft's inequality, which is given by equation 5 before, and whose expected length, L star, which is sum of I from 1 to m, pi Li star, is less than the expected length of any other prefix code. Now, solution is, if I write the average expected length of the code word as sum of I from 1 to m pi Li, then my problem is to minimize L over all integers L1, L2, Lm, which satisfy also the Kraft's inequality condition. Sum of I from 1 to m, d to the power minus Li, must be less equal to 1. Now you might know from mathematics, a good strategy for this one, it is to use the so-called Lagrange multiplier method, which means you have to construct a function like this, which is called J, here, which is sum of I from 1 to m pi Li plus some lambda, sum of I from 1 to m d to the power minus Li. The first, it is the function which is subject of minimization. And the second term, it is the condition that the lengths must satisfy, which is Kraft's inequality condition, times some multiplier, the second term, which is called Lagrange multiplier. Now, the procedure goes as the following. First, we take the derivative with respect to subjectives, which are LIs, and equalize it to 0. So we take the partial derivative of J with respect to Li. Then you could notice that from the first term, we are left just with Pi. From the second term, you'll get minus lambda d to the power minus Li log with base E of d. And we equalize this to 0. How we get to the second term? By taking the derivative of the second term on J, it is as the following. Take the derivative, partial derivative with respect to Li of the log with base E of d to the power minus Li. Then this is equal to, from mathematics, 1 over d to the power minus Li times derivative of d to the power minus Li over of respect to Li. Then this is equal to minus log with base E of d, then the partial derivative of Li with respect to Li, which is equal to 1. And this is equal to minus log with base E of d. And it is this one that we have derived this equation on here. Now, if we solve this one for d to the power minus Li, then we get the following. D to the power minus Li, it is equal to the Pi probabilities over lambda times log with base E of d. Now we take this one and substitute it in the Kraft's inequality constraint. And we get the following. Sum of phi from 1 to m d to the power minus Li, it is equal to sum of phi from 1 to m d to the power minus Li, it was equal to Pi over lambda log with base E of d. And this must be less equal to 1, which implies from this equation here that lambda itself, you could show this easier, all right? On this one, on this equation here, 1 over lambda log with base E of d does not depend on I. So I can bring it outside. Then sum of phi from 1 to m p of phi gives you 1. Then from this one, you could get that lambda itself, it is bigger or equal to 1 over log with base E of d. Therefore, d to the power minus Li, if I replace you have it Pi over lambda log with base E of d, I replace lambda by this inequality, then you get that this is less equal to P of phi over 1 over log with base E of d times log with base E of d. Log with base E of d cancels out, then you get simply Pi. Solving it for Li, then you get that Li star are greater or equal to minus log with base d of P of phi. So we found the solutions, all right, for Li, optimal Li star. Right? Now we come to a theorem, which is actually eventually what we just proved. The expected length L of any instantaneous DRE code for a random variable x is greater than or equal to the entropy HD of x. This will give us a lower bound for the optimal expected length. L, it is greater or equal to HD of x. Equality holds for P of phi exactly equal to d to the power minus Li. Now, using the results of the optimized code lengths above, or we have that L of phi is greater or equal to minus log with base d of Pi. If we multiply both sides by Pi and sum up according to y, then we get the following. Sum of phi from 1 to m P of phi Li greater or equal to minus sum of phi from 1 to m P of phi log with base d of P of phi. Now you could notice that the left-hand side gives you the expected length of the code word, and the right-hand side gives you the Shannon entropy with base d. It is clear that the equality holds for Li equal to minus log with base d of Pi, or P of phi, it is equal to d to the power minus Li. Now, we give some a new definition here. A probability distribution is called d-etic if each of the probabilities is equal to the d to the power minus n for some n. Based on the previous theorem, where L is greater or equal to entropy with base d of x, where the equality holds for p of I equal to d to the power minus li, that is, if and only if the distribution is d-etic. Now, let's Li star, a theorem now, L2 star, Lm star be optimal code word lengths for the source distribution P and the D-array alphabet, and let L star be the associated expected length of an optimal code. So this means that L star, it is sum of I from 1 to m, P of I, Li star. Then L star, it is greater or equal to hd of x and rigorously less than hd of x plus 1. So now we are giving both the lower and the upper limit for the optimal expected length of the code word. Now, how you could prove this one? We found that Li stars are greater or equal to minus log with base d of P of I. Since Li star gives a length, must be an integer number. To obtain an integer number, then we take the right-hand side and assign it as a floor or the seal. I've taken the seal function. So Li star, it is equal to minus the seal of log with base d of P of I. Using the definition of the sealing function, we know that Li star, it is greater or equal to minus log with base d of P of I and rigorously less than minus log with base d of P of I plus 1. We multiply both sides by P of I and the sum up over all i's. Then the left-hand side will give minus sum of I from 1 to m, P of I log with base d of P of I. Less equal to sum of I from 1 to m, P of I Li star, less than minus sum of I from 1 to m, P of I log with base d of P of I, plus sum of I from 1 to m, P of I. Now, the term on the left-hand side gives the Shannon entropy with base d of x. The term in the middle gives the optimal expected length of the code, L star. Then the first term on the right-hand side gives the Shannon entropy with base d of x. And the last term gives you 1 because it's normalization condition of the P of i's. And this is the proof of the theorem. It can be seen that there is at most 1 bit of overhead. Now, this is due to the fact that log with base d of 1 over pi is not always an integer number. So it is from mathematics on here. That overhead per symbol can be reduced by spreading it out over many symbols, and this will be shown on the next slide. Now, consider x1, x2, xn be a sequence of n symbols from x drawn independently, identically distributed according to P of x. Let xn, x to the power n, this sequence x1, x2, xn, which is an n tuple from the set chi n. And this is one realization of x1, x2, xn random variables. By definition, let L of n be the expected code word length per input symbol. That is, this is the, if L of x1, x2, xn is the length of the binary code word associated with this n tuple x1, x2, xn, then Ln, it is 1 over n sum of P of x1, x2, xn times L of x1, x2, xn, which is equal to 1 over n expected value of L, x1, x2, xn. Now, using the bounds of the optimal code length, we have the following. The joint entropy of x1, x2, xn, it is less equal to the expected value of L of x1, x2, xn, rigorously less than joint entropy of x1, x2, xn plus 1. Since x1, x2, xn are IID, then we have showed this on the previous lectures, then the joint entropy, it is equal to the sum of I from 1 to n h of xi because of the independence. Because of being identical, then this sum, it is equal to n times entropy of one of the random variables, let's say x1, or n times the entropy of x in general. Therefore, if we divide on the equation 1 on this slide, both sides by 1 over n, since 1 over n is a positive number, the signs of inequality does not change. Then you get 1 over n joint entropy less equal to 1 over n expected value of L less than 1 over n joint entropy plus 1 over n. Now, if you replace the joint entropy with n times h of x, then you get h of x less equal to ln less equal to h of x plus 1 over n. You should notice here that h of x actually, right, it is also the so-called entropy rate. Now, again, using the bounds of the optimal code, we have the following. H of x1, x2, xn less equal to expected value of L less the joint entropy plus 1. Again, divided both sides by n. All right. But now we consider the case that the x1, x2 are not necessarily IID. Then you will have 1 over n joint entropy less equal to ln less 1 over n joint entropy plus 1 over n. If the stochastic process is stationary, then we take the limit when n goes to the infinite of 1 over n h of x1, x2, xn, and this will give me the entropy rate exactly. Therefore, in the limit for large n, we obtain that ln star, the optimal code length expected, is greater or equal to the entropy rate and less rigorously than entropy rate plus 1 over n. I could notice that if n goes to the infinite, then the 1 over n goes to 0. And then in that case, the overhead, it is removed. Then this comes the theorem that follows. The minimum expected code word length per symbol satisfies this equation, 1 over n joint entropy less equal to ln star less than 1 over n times the joint entropy plus 1 over n. Moreover, if x1, x2, xn is a stationary stochastic process, then the ln star converges to entropy rate of the process if n goes to infinite, right? Now, this was shown on the previous slide. It is easy to follow this one. Now, around codes. The expected length under P of x of the code assignments L of x, which was equal to the CL of log with base 2 of 1 over Q of x, satisfies this equation. H of P plus relative entropy between P and Q less equal to the expected value with probability distribution P of x of L of x less equal to H of P plus relative entropy between P and Q plus 1. Now we can prove this one. Now the wrong code, just a comment, a wrong code would mean, all right, a wrong calculation of the expected length if the true distribution, probability distribution is P of X, but we assume it is Q of X. The expected code length, it is this one. It is sum of all x's from chi P of X, CL of log with base 2 of 1 over Q of X. Now I use the property of the CL function, and this is less than sum of all x's P of X times log with base 2 of 1 over Q of X plus 1. Then this is equal to sum of all x's P of X log with base 2 of P of X. So I multiply and divide by P of X. P of X over Q of X times 1 over P of X plus 1. Then I write this one as a sum of two terms. One log with base 2 of P of X over Q of X, and the other one log with base 2 of 1 over P of X. Now the first term, sum of all x P of X log with base 2 of P of X over Q of X, gives me the relative entropy between P and Q. Second term gives me the Shannon entropy with proper distribution P of X plus 1. So I showed here the right-hand side of the equation 11. To take the left-hand side of the equation 11, we use the other property of the CL function. CL of X, it is greater or equal to X. So I'll have expected value of L of X, sum of all x P of X, CL of log with base 2 of 1 over Q of X. It is greater or equal to sum of all x P of X log with base 2 of 1 over Q of X. Now again, I use divide and multiply by P of X, and I split log with base 2 on two terms, log with base 2 of P of X over Q of X, plus log with base 2 of 1 over P of X. And I obtain the third line, sum of all x P of X log with base 2 of P of X over Q of X, plus sum of all x P of X log with base 2 of 1 over P of X. The first equation gives me the relative entropy between P and Q, and the second equation gives me the Shannon entropy with proper distribution P. Then I prove the both sides of the equation 11 before. Next, we are going to talk about the Hoffman codes. First, we give the Hoffman code theorem. For any distribution, there exists an optimal instantaneous code with minimum expected length that satisfies the following properties. The lengths are ordered inversely with probabilities. That is, if P of J greater than P of K, then L of J is less equal to L of K. The two longest code words have the same length. Two of the longest code words differ only in the last bit and correspond to the two last likely symbols. We are going to prove this theorem one by one. First part, consider an optimal code CM, where P of J it is greater than P of K. Now consider another code, CM prime, with J and K of C of M interchanged. Then we'll have to calculate the difference between the expected lengths. One according to the CM prime code, and the other one according to the code words CM. Then I have L of CM prime minus L of CM. Now, since the L of CM, it is the optimal one, so this means that it is the smallest possible. So the LCM prime can only be equal or greater than L of CM. So this means that this difference, it is greater or equal to 0. Moreover, this is equal to, for the LCM prime, this is equal to the sum of all i's, P of I, Li prime. Minus, for the LCM, I have sum of all i's, Pi, Li. Now you should notice, then CM prime, it is obtained by CM by just exchanging the code words of the J and the K. So I will have here, for the LCM prime, I have PJLK plus PKLJ, which are different from the CM. And all the others are equal. Now for this, the jth and the kth one, for the CM, this sum, it is equal to PJLJ plus PKLK, normal way. Because on the CM prime, LKE becomes LJ and vice versa. Now you could rearrange this one as PJ minus PK times LK minus LJ. Now since PJ minus PK is greater than 0, then this implies that LK minus LJ is greater or equal to 0. Because you wanted all these difference to be greater or equal to 0. Or it means that LK is greater or equal to LJ. And this is what we wanted to show. Second proof, we can, for the second part, we can trim the code words. If the two longest code words are not the same length, then we can delete the last bits of the longer code word, preserving the prefix property. For the property number 3, this property can be achieved by rearranging the code words, right, from the smallest to the largest code length. Right? Now, as a remark, the Hoffman codes are such that if P of I is greater or equal to P of 2 greater or equal to, and so on, P of M, then there exists an optimal code with length L1 less equal to L2, and so on, less equal to LM. Moreover, the last two code words, namely C of XM and C of XM minus 1, differ only from the last bit. How to construct the Hoffman codes? For example, consider P a probability distribution. P of 1, P2, P of M, where P1, it is greater or equal to P2, greater or equal to, and so on, greater or equal to PM. And this is a property mass function for an alphabet of length M. The Hoffman reduction is defined as P prime, which is P1, P2, up to P of M minus 2. However, P of M and P of M minus 1 are summed up. P of M minus 1 plus P of M, which is a property mass function over an alphabet of size now M minus 1. Cm star of P is optimal code for P, and Cm minus 1 star of P prime is the optimal code for P prime. How you could do this practically? Consider this canonical code, Hoffman code, with P1 greater equal to P2 greater equal to P5. All right? And as you can see, L1 it is equal to 1, is simply 0. Here, right? Then I have L2 it is equal to 3, and there's P2, and it is 1, 0, 0. L3 it is equal to 3, it is the code 1, 0, 1, and P3. P4 and P5 are 1, 1, 0, and 1, 1, 1. Now you could see that P4 and P5 have the same length of the code words, and the code words changes from the last bit. One it has 1 and the other one 0. So this is a Hoffman code. Now you could construct an optimal code, Hoffman code from this one. Now, as we said, we sum up the two lowest probabilities, P4 plus P5. All right, then, all right, we obtain for P1, P2 and P3 remain the same. However, P4 plus P5, if we sum up, then this will reduce to the code 1, 1. The last bit, it is ignored. Then you have this branch, 1, 1, with property P4 plus P5. Now you could notice, then I want to have Hoffman code. So whenever P of 1, it is greater or equal to P of 2, greater or equal to P of 3, greater or equal to P4 plus P4, and so on, then the L1 must be less equal to L2 and so on. But L1, it is equal to 0. But L2 and L3 are equal to 3. L of P4 plus P5 is equal to 2. So I have to rearrange it. All right? So to rearrange it, you bring it like this. So you have to bring the code length with property P4 plus P5 in the second place, because it has to have a length of 2. Right? Now it cannot come on this one. It cannot come as 1, 1. Why? Because it would have come on here. But if it comes on here, then because I have to have a prefix code, all these branches that are descendant to it would be deleted. But I cannot delete it on here. So I have to have P4 plus P5 on here. It has to be 1, 0. Then I delete all the descendant of it. Then the next one becomes 1, 1, 1 and 1, 1, 0. And you can see that this is Hoffman code, because P2 and P3 changes from the last bit. One has 1 and the other 1, 0. So this is now optimal Hoffman code with M-1 symbols. Now, another code that we are going to introduce is the so-called Shannon-Fano-Elias code. For this one, we refresh some knowledge of the probability in statistics. First, we'll give the concept of probability distribution. Consider the alphabet set chi of numbers 1, 2, and m, up to m. Let P of x be a property mass function such that the P of x is greater than 0 for every x from chi. Probability distribution function is defined as the following. F of a, it is sum of all x's less equal to a P of x. If you want to plot this one, this P of x could be some probability like this. So you have P of 1, some value between 0 and 0.1 here, 2, 0.1, 3, in between 0.1, 0.2, and so on. Then if I have f of x, then f of x would be equal to sum of all x is less equal to a P of x, then it would look like this. For the first one, you get only the P of 1. For the second one, you get P of 1 plus P of 2. P of 1 plus P of 2 plus P of 3 will give you this one. P of 1 up to P of 4 will give you this side. P of 1 plus P of up to P of 5 will give you this side. Then P of 1 plus up to P of 6 will give you just 1. And it is this one. Now, consider modifying the probability distribution as the following. We consider f bar now of a as equal to sum of all x's, but less rigorously than a P of x, plus 1 over 2 P of a. Now you could notice that this f of bar has the following properties. It denotes a probability distribution because it is a number between 0 and 1. It is the step size, it is P of x, similar to the also f of a. F of a bar, it is such that whenever a it is different from b, f bar of a it is also different from f bar of b. So if you see it as a function, this is one-to-one function. Therefore, it is also on 2. Therefore, the inverse exists. And we denote this f bar minus 1 of x. And can be defined in such a way. If we know f of bar of x as, all right, f bar of x, then f bar minus 1 of some u, it is equal to x, where u, it is a number between 0 and 1. Therefore, also f of bar of x can be used a code for x. All right. Here it is how the f of x and f bar of x are defined. All right. So on here on the columns, on these columns on red and yellow, so this gradient, I've plotted f of x. Now you could notice down that the f bar of x, it goes right in the middle. For example, if I have f4, f of x, which is this in black here, this line. Now f bar of x, it is this one in red. So you could see now it is between fx minus 1 and f of x. And it is right in the middle. Right? If the distance between f of x and f of x minus 1, it is p of x. So it is also the difference between f bar of x minus f bar of x minus 1. Now, you could notice that f bar of x, it is a probability distribution because it is a number between 0 and 1. And since it is a number between 0 and 1, it can be expressed as a binary number using an infinite in general number of bits. So you could say that f bar of x can be expressed as a 0.y1, y2 up to yl of x. y1, y2, and so on, yl are bits, all right? So are numbers between 0 and 1. And L of x gives the length of the code for x. Therefore, you can write that f bar of x, it is approximately equal to the floor of f bar of x with length L of x. This is the same as saying, taking this infinite number of bits and concatenating it to some length L of x. And this is why you get approximation. So this means that this is a number 0.y1, y2, yl of x. By definition, the difference f bar of x minus the floor of f bar of x with length L of x, it is smaller than 1 over 2 to the power L of x. So if L of x, it is equal to the CL of log with base 2 of 1 over p of x plus 1, then p of x over 2, which is equal to the f bar of x minus f of x minus 1, it is equal to the greater than 1 over 2 to the power L of x. So this implies that the floor of the f bar of x with length L of x lies within one step corresponding to x. Since L of x, it is equal to the CL of log with base 2 of 1 over p of x plus 1, then this gives the number of bits to represent x. Then the expected length of the code, it is equal to the L, it is equal to sum of all x, p of x, L of x. Using the properties of the ceiling function, CL of x, it is greater or equal to x less than x plus 1. Then we get that CL of log with base 2 of 1 over p of x plus 1, it is greater or equal to log with base 2 of 1 over p of x plus 1, less than log with base 2 of 1 over p of x plus 2. We multiply both sides by p of x and sum over all x's. Then the left-hand side gives you entropy of x plus 1, less equal to the term in the middle gives you the expected length of the code word L, and the right-hand side gives less entropy of x plus 2. So you could notice now that for the Shannon-Fanos-Elias coding, there is an overhead on the lower bound plus 1 and on the upper bound plus 1. Right? Because plus 1 gives you plus 2. And this is actually the drawback compared to the Hoffman code. Hoffman code are more optimal. Right? That's what, because the L, it is smaller compared to the Shannon-Fano-Elias coding. However, the Shannon-Fano-Elias coding is quite simple to understand and even to program it. For example, this table illustrates it. Suppose that I have a random variable x, which takes the value 1, 2, 3, and 4. With this probability distribution, 0.25, 0.5, 125, 0.125. Then f of x, it is p of 1, 0.25. Then p of two, f of 2, it is equal to p of 1 plus p of 2, which is 0.75. F of 3, it is p of 1 plus p of 2 plus p of 3, 0.875. Then p of 4, it is sum of all p's, which is 1 in that case. Then f bar of x, it is equal to the, first it is p of x over 2. F of 1, it is p of 1 over 2, which is 0.125. Then f bar of 2, it is equal to p of 1 plus p of 2 over 2, right? Which is equal to 0.5, right? 0.25 plus 0.5 over 2, which gives you 0.5. Then f bar of 3, it is equal to p1 plus p2 plus p3 over 2, which is 8,125. Then f bar of 4, it is equal to p1 plus p2 plus p3 plus p4 over 2. Then it is 0.9375. Then for 0.125, we convert this one into the binary number. Then you get 0.001 binary number. Then from this one, we get what is after the decimal point, which is 001. And this will give me Cm of 1, 001. And the length is 3. 0.5 converts into the binary as the number 0.10. Then we get the 1 and 0 after the decimal point as the code word for C of 2. Then the length is 2. 8,125 converts into the 0.1101. Then 1101, it is the code word for 3, x equal to 3, and the length is 4. Similarly, 0.9375 converts into the 0.1111. Then the code word, it is 1111 for x equal to 4, and the length is equal to 4. What you should know from this lecture, you should know about the data compression codes, the properties, and the definition that we gave. You should know about the Kraft's inequality and optimal codes, and you should know about the Hoffman codes and Shannon-Fano-Elias code. Some references are the same as the last week. So thank you and for your attention. I'll see you next lecture.